surface tension, and viscosity. If we didn't have intermolecular forces, everything would be a gas, and there would be no life, right? It would just be this big mix of gases. So intermolecular forces are pretty important. We see evidence of them in several characteristics of liquids. Liquids have something called surface tension and viscosity, and those are the result of intermolecular forces. This is a picture of a paperclip floating on water. Paperclips are made out of metal, right? Does metal normally float on water? No, it doesn't. And yet, if you're careful, you can float a paperclip or a needle on water. You may have seen water bugs skating around on the water, and you're like, how do they do that? Right? Yeah, put some soap on it, right? And poof, they sink real fast. The water here is held up by the surface tension. It's almost like there's a skin on top of the water, this little tiny layer that resists anything going through it. Now, if you have something that's large, the force of gravity is going to pull it through there. But if you have something like a paperclip that's light, the surface tension can hold it up. You can't do this on something like gasoline or rubbing alcohol or whiskey or something, because those things have weaker intermolecular forces than water does. And if you put a drop of soap or sprinkle some salt or pepper on here, it will also break the surface tension and cause the paperclip to sink. So here we're looking at an illustration of water molecules. So this water molecule is having interactions with its neighbors. Right? So we're looking at this in 2 dimensions instead of 3, but this one's interacting with 6 neighbors. And this one on the surface doesn't have those other 2 up here to interact with, so it's only interacting with 4 neighbors. But essentially it's getting pulled down. So this has a net inward force, whereas this one is experiencing a force that's in all directions. So this guy is being pulled inward. That creates almost like a skin at the top of, have you ever left pudding in the refrigerator too long and it gets a little skin on top, right? It's like, ew, nasty, but I'm really hungry, so I'm just going to peel it off and eat the pudding underneath. So it's like the skin on pudding. Water drops are spherical, although when gravity pulls on them here, I don't know if that's a piece of grass or a needle. It's hard to tell. But here's a droplet of water. The reason that it's not a perfect sphere is because gravity is pulling down on it. If you catch a picture of water falling, you're going to see that it's more spherical. It forms spheres because of that surface tension. The water molecules on the edges of the drop of water are being pulled in. And so water is going to take on a shape in small quantities that minimizes the surface area. This is a cool picture. Astronauts on the space shuttle playing around with water. So this is a giant drop of water. And it's got intermolecular forces. It all sticks together. And because there's no gravity, this is this big blob of water. You could throw water balloons at each other without having the balloon part, right? I can't even imagine what these guys have done up there. It sounds pretty fun. Well, any questions about surface tension? Another property of liquids is viscosity. So viscosity is the resistance of a liquid to flow. Liquids flow, right? You can pour a liquid. But some liquids pour faster than others. Think honey versus water, right? Honey pours, but it does so very slowly because it has a high viscosity. We think of it as being thick, right? It doesn't pour very well. Motor oil. Motor oil is more viscous than gasoline. Gasoline is not very viscous at all. Now, you know, if you're a safe, good person, you probably haven't played around with gasoline. But maybe you saw when you were filling the lawnmower, you see the gas pouring, and it looks a little different than water when it pours, right? It seems thinner somehow, and it is. So viscosity is caused by these intermolecular forces between the molecules in the liquid. If the forces holding them together are stronger, then it can't flow as easily, because when the particles move relative to each other, they're breaking off those intermolecular forces with the neighbors that they were next to and making new ones with new neighbors. But it involves breaking forces. If the forces are strong, it's going to be difficult to break those. And so you can think of a liquid getting thicker and thicker and thicker. It's almost approaching a solid, right? Solids don't flow. Do you know that glass flows?
Is there a direct relationship between viscosity and evaporation?
Yes, there is a relationship between viscosity and evaporation. We'll get to that. If you look at the windows in really, really old buildings, they are thicker at the bottom and thinner at the top. They were not made that way. Over the course of hundreds of years, the glass is slowly, incredibly slowly, running down. Really, really slowly. Because the intermolecular forces between the glass particles are pretty strong, and it's holding it together. But, you know, you take like maple syrup or honey, you stick it in the refrigerator, right? And you get it cold. Does it get thicker or thinner? It gets a lot harder to pour, right? Because then the intermolecular forces are even stronger because the lower temperature, the lower movement of the particles. Here's a picture. I hope you guys had breakfast. That looks really good. Better than the granola bar I ate on the freeway.